Today, we are diving into something truly monumental. It's a huge leap forward in the quest to build a quantum computer that can actually change the world. For years, the entire field has been pushing towards this one critical tipping point, and a brand new paper from Google's quantum AI team says they finally crossed it.
It's a totally fair question, isn't it? We hear all this incredible stuff about what quantum computers are supposed to do, for medicine, for new materials, for AI. So where are they? What's the big holdup?
Well, it really boils down to one single massive problem. See, the basic building blocks of these machines, the qubits, they're unbelievably fragile. I mean, the slightest little vibration, a tiny change in temperature, and poof, they get knocked off course and make a mistake, an error. And the scale of this problem, it's just staggering. Right now, our very best physical qubits have an error rate of about 0.1%. I know, that sounds pretty good, right? 99.9% accurate? But here's the thing. To run the algorithms that could actually change the world, we need error rates that are literally billions of times lower. The gap between where we are and where we need to be is just immense.
So how in the world do you solve a problem that big? Well, for decades, the theoretical answer has been this really cool idea called quantum error correction. And the basic concept, it's surprisingly simple: teamwork.
The idea is, instead of trusting one single, fragile physical qubit, you create what's called a logical qubit. Just think of it like a team of physical qubits, all working together, all hands on deck, to protect one single piece of information. So yeah, any individual player on that team might mess up, but the team as a whole can spot the error, fix it, and keep on going, creating one super robust, reliable unit. And that's formally what quantum error correction, or QEC, is. You spread the information out, and you build the system of checks and balances to constantly monitor the team for any mistakes. And here's the magic trick. You can find and fix the errors from the individual physical qubits without ever actually looking at and destroying the precious quantum data that the logical qubit is holding. It's brilliant. But there's a catch. And for a long time, this was a huge problem with the whole idea. See, it doesn't always work. In fact, sometimes adding more qubits to your team just adds more noise and makes everything worse. It all comes down to hitting a critical tipping point. This quote from the paper really gets to the heart of it. It says that this amazing error suppression, the part where things get better and better as the team gets bigger, that only kicks in if the quality of your individual physical qubits is already good enough. They have to be performing below a certain error threshold. Think of it this way. If your team is made of pretty reliable people, adding more players makes the team stronger, right? But if your team members are all kind of chaotic and prone to making mistakes, adding more people just adds more chaos. That error threshold is the make or break line. If you can get below it, you have a scalable path forward. If you're stuck above it, well, you're stuck. And this has been the billion-dollar question just hanging over the entire field for years. People have gotten close, they've shown hints of it, but no one had ever built a system and been able to say, with cold, hard data to back it up, yes, we are definitively operating below the threshold. That is, until now. And that brings us to this breakthrough. In their latest work, using a whole new generation of quantum processors, the Google team has delivered the first definitive experimental proof of a quantum error correcting system that is operating below that critical threshold. And this is the smoking gun, the number 2.14. They call this lambda, the error suppression factor. It basically measures how much better the error rate gets as you add more qubits to the team. Now, a lambda of 1 means you're just breaking even, but anything at all greater than 1 proves you're below the threshold and you're actively crushing errors. A value over 2, that means the error rate gets cut by more than half every single time you scale up. This chart right here shows you what that looks like in the real world. You're seeing the logical qubit's error rate as they make it bigger, what scientists call the code distance. It's basically how strong the team is. And as they grow the team from a size 3 to a size 5 to a size 7, look at that. The error rate just drops. This is it. This is the holy grail of quantum error correction in action. Making the team bigger actually demonstrably makes it better. And it's not just about having fewer errors when you do things. The logical qubit, the team, is also just fundamentally more stable. Their biggest logical qubit actually survived for 2.4 times longer than the very best individual physical qubit they used to build it. The whole is truly demonstrably greater than the sum of its parts. So the key takeaway here is absolutely huge. This isn't just some small, incremental improvement. This is the first concrete proof that the entire roadmap for building a useful, fault-tolerant quantum computer is actually viable. It can be done. But okay, let's be real. Crossing this threshold is kind of like reaching base camp on Mount Everest. It's a massive, massive achievement, for sure. But the summit is still a long, long way off. And what's cool is that this result has also shined a bright light on the next set of challenges that scientists and engineers need to tackle. One of the most powerful things about this work is that they can now create an error budget and see exactly where the leftover mistakes are coming from. Turns out, the biggest culprit is errors in the 2-qubit gates, the operations that let 2 qubits talk to each other. They also found that about 17% of errors come from sneaky sources, like information leaking out of the qubit. This is basically the new engineering to-do list for the entire field. And just to give you a sense of the scale of that to-do list, it's significant. To get to an error rate of 1 in a million, a key milestone for useful algorithms, they calculate that they'll need to scale up to a distance 27 logical qubit. That would take nearly 1,500 physical qubits all working in perfect harmony just to create one of these ultra-stable logical qubits. And there's a new mystery on the horizon. In other really deep experiments, they uncovered a completely different kind of error. These are rare but catastrophic, bursts of noise that seem to happen about once an hour. These weird events create a new error floor at an incredibly low level, but it's a floor that could still block future progress. Figuring out what causes these bursts and how to stop them, that's the next frontier.
So here's the bottom line. By finally crossing this error correction threshold, the whole game has changed. The fundamental scientific question has shifted. Researchers have now demonstrated a viable, scalable path to a fault-tolerant machine. The challenges that are left, and they are enormous, are now mainly problems of engineering and of scale. The conversation is no longer about if we can build one, but about how fast we can climb the road that is now finally clear ahead of us.